हुन्छ सर, गुड, रेकर्ड सुरु भयो। सम्पूर्णलाई स्वागत गर्न चाहन्छु। यस कार्यक्रमको सभापतित्व गरिदिनु हुन यस समाजका उपाध्यक्ष डाक्टर लेखनाथ मिश्र सरलाई अनुरोध गर्न चाहन्छु। लेखनाथ सर।
नमस्कार सबैलाई।
आजको यस टक प्रोग्राममा स्पिकरको रूपमा यस समाजका गहनाका रूपमा उदयमान भौतिकशास्त्री तथा यस समाजका भूतपूर्व सचिव प्राडा नारायण प्रसाद अधिकारीज्यूलाई हार्दिक आमन्त्रण गरेका छौँ। हाम्रो निमन्त्रणालाई सहर्ष स्वीकारी दिनुभएको र यस कार्यक्रमको शोभा बढाइदिनु भएकोमा प्राध्यापक डाक्टर नारायण प्रसाद अधिकारीज्यूलाई हार्दिक धन्यवाद दिन चाहन्छौँ। नेपाली भौतिकशास्त्रीको सामु प्राध्यापक नारायण अधिकारी आफैमा एक परिचय हुनुहुन्छ, तथापि उहाँको ब्रिफ सिभी वाचन गरिदिनु हुन यस समाजका एडिटर डाक्टर होम बानिया सरलाई आग्रह गर्न चाहन्छु। होम सर। होम सर अनम्युट गरौँ।
धन्यवाद मल्लिक सर। नमस्कार सबैमा, रेस्पेक्टेड सरहरू। म हाम्रो प्रोफेसर डाक्टर नारायण प्रसाद अधिकारी सरको सिभी पढ्न गइरहेको छु। His name is Professor Dr. Narayan Prasad Adhikari, Central Department of Physics, Tribhuvan University, Kathmandu. He had completed his master in 1996, physics from Central Department of Physics, Tribhuvan University. His master thesis entitled size of his master thesis entitled on size effect in metal cluster under the supervision of Professor Dr. Devendra Raj Mishra sir. And then he had completed his diploma in 1998 on condensed matter physics from the Abdus Salam International Center for Theoretical Physics, Italy, on secured GPA 3.09. Thesis entitled at that time is calculation of the energy in two weakly coupled Bose-Einstein condensate under the supervision of Professor Stefano Fantoni. Likewise, Professor Adhikari has completed his PhD in 2001, entitled Physics from University from Physics from Martin Luther University, Germany. Thesis entitled on interfacial property and phase behavior of unsymmetry polymer blends under the supervision of Professor Ernst Stumby. And then finally postdoctoral experience. He has postdoctoral experience in October 2000 on August 2002, Rice University, Austin, and from Texas, USA, under the supervision of Professor Jacqueline Gobas. He has on more experience on September 2002, July 2004, Rensselaer Polytechnics Institute, Tuari, Newark, under the supervision of Professor Sanat Kumar. On more experience he had during this time on August 2004, December 2005, Max Planck Institute for Polymer Research, Mainz, Germany, under the supervision of Professor Kurt Kimmerer. Working experience as a member of, he has a member of physics faculty at CDPTU from 1996, ICTP associate member from 2009 to 2015, and from 2017 to till date now, up to now. In brief, Lee, he has he's an associate member from 2009 to 2015 to till date. Thank you, sir. Thank you very much.
Thank you very much, Home sir, for Narayan sir brief CV. नारायण सर को परिचय उहाँ आफैमा हुनुहुन्छ, केही भनिरहनु पर्दैन। अब मैले यो फ्लोर चाहिँ नारायण सरलाई हस्तान्तरण गरेँ। नारायण सर प्लिज।
Okay, namaskar. Good evening. I would like to thank Nepal Physical Society for providing this opportunity to discuss about one small talk about computational physics in Nepal. मैले थोरै computational physics in Nepal कसरी डेभलप हो भन्ने कुराहरू फोकस गर्छु। साथसाथै few projects, how are they developing, how are they going on, त्यसको बारेमा थोरै ब्रिफ छलफल गर्छु। त्यो छलफल गर्दाखेरि it's a bit kind of random walk, so it could be difficult to make coherent conclusion, but still we can make conclusions in each part of the projects. So briefly, I will discuss what is computational physics and why do we need it. How did it start in Nepal? Development of computational lab in our department. Computational physics to understand nanomaterials, to understand our daily life, pharmaceuticals, biomolecules, DNA-protein interactions, protein-protein, SARS-CoV, human-astro interactions. These are our current interests. Actually, I will focus more on these last topics. Okay, actually, computational physics complements both theoretical physics and experimental physics. What happens, you take any material from nature and carry on an experiment. That's the real thing actually we measure. That is quantitative measurement of any physical phenomena, what we do. To understand that physical phenomena, and then from that modeling, with certain approximations, we will be able to solve those equations.
Unmute गरेर फेरि प्लिज
नारायण सर अनम्युट गरेर हजुरले गर्नुपर्ने हो।
नारायण सर
अधिकारी सर हजुरले अनम्युट गरेर गर्नुपर्ने हो। हजुरको म्युट भयो नारायण सर।
यो सुरुबाटै म्युट हो?
होइन सर, ठीक छ, अहिले ठीक छ।
ठीक छ यो?
ठीक छ सर।
I mean, from where I did miss second first
outline sir, yes, computational phase, what and why.
Okay, what we do, we take certain materials, we carry on experiments and find out its properties. Quantitative measurement garchau experimentalistले. To understand that one, to make it more predictive, you must be able to solve certain equations to understand that phenomenon. So, त्यो बुझ्नलाई हामीले केही इक्वेशन्सहरु लिएर सल्भ गर्दाखेरि एनालाइटिकली सल्भ गर्न सक्ने हुन सक्छ, कहिलेकाहीँ नहुने चान्स बढी हुन्छ। मोस्ट अफ द नन लिनियर इक्वेशन्स एनालाइटिकली सल्भ गर्दाखेरि र even quantum mechanics ma, if we talk about any problem like say starting from helium atom itself, we cannot solve that exactly analytically. So from there you need to take help of computational physics. So computational physics हामीले without approximation solve गर्छौं र theoretical physics र experimental physics को केही डिफरेन्स आएको रहेछ भने र फेरि computational र experiments को डिफरेन्स आयो भने देखि मोडलमै प्रब्लम छ भनेर पहिले बनाएको मोडलमा टेस्ट गर्न सक्छौं भने देखि computational physics र theoretical physics मा प्रब्लम छ अग्री हुँदैन भने देखि यहाँ युज गरेको एप्रोक्सिमेसन मा प्रब्लम छ भनेर त्यहाँबाट हामीहरु solve गर्न सक्छौं. So all these three disciplines are actually growing up तीनटै डिसिप्लिनहरुको बीचमा देयर इज नो कम्पिटिसन बट one complements another हो। यो तीनटा डिसिप्लिन हामी जे फिजिक्सको भन्छौं एउटा अर्को भन्दा सुपिरियर हुने भन्ने कुरा होइन, एउटाले अर्कोलाई कम्प्लिमेन्ट गर्ने हो। All the three are taken as complementary and integrated parts of carrying on any physics phenomena, to understand any physics phenomena. So नेपालमा यो कम्प्युटेशनल फिजिक्स कसरी सुरु भयो भन्दाखेरि 1999 को कोर्स हेरौं एमएससी फिजिक्स को भनेदेखि त्यहाँ हार्ट्रीफोक सम्बन्ध थियो र हिलियम एटमको पनि हामी हार्ट्रीफोकबाट सल्भ गर्ने कुराकानीहरू छन्। सिम्पल सिस्टम्स बाइ ह्यान्ड गर्न सक्ने र त्यसलाई न्युमेरिकली सल्भ गर्न सक्ने कुराहरू केही सुरु भएको थियो। बट प्रोफेसर तारादास फ्रम सुनी अल्बानी State University of New York, Albany, he helped to understand more complex systems using Hartree-Fock को के हुन्छ भन्दाखेरि what you do, Hartree-Fock equation as such cannot be solved in computers. They are converted to algebraic equations, so-called Ruthan's equations. Those Hartree-Focks were converted to Ruthan's by Professor Taradas, actually at our department. That's what I'm saying. And उहाँले Hartree-Fock र MP2 हरु Hartree-Fock plus MP2 तो गर्ने गाउसियन यहाँ डिपार्टमेन्ट ल्याउने र त्यति बेलाको हाम्रो फ्याकल्टीहरुलाई ट्रेन गर्ने देखि स्टुडेन्ट्सलाई ट्रेन गर्ने सबै काम सुरु त्यहाँबाट भएको कम्प्युटेशनल फिजिक्स। Almost all the faculties of that time at CDPTU were involved in computational physics. Professor Das not only helped develop here Gaussian but also trained few faculties, at least 2 जना यहाँको फ्याकल्टीहरुले as a Fulbright fellow उहाँसँग पोस्टअप गर्नुभएको प्रोफेसर नन्दबहादुर महर्जन र प्रोफेसर सीताराम ब्याउत। After rejoining CDPTU in 2006, I also involved in the same project. However, we needed a computational physics lab. काम गर्नलाई ल्याब चाहिएको थियो। एउटा प्रिन्टर, एउटा PC, generator was obtained from ICTP in 2009. ICTP gave certain money to CDPTU to purchase those 3 things. That was something really good to start. त्यो बेलासम्म हाम्रो स्टुडेन्ट्सलाई हामीले ल्यापटप अथवा उनकै PC मा काम गर्नलाई इन्करेज गर्थ्यौं। एउटै PC भए पनि हाम्रो डिपार्टमेन्टमा छुट्टै डेडिकेटेड फर कम्प्युटेशनल फिजिक्स कामको लागि सुरु भयो। We wrote proposal to MOEST, सक्सेस भयो, but it was not enough to get Gaussian हाम्रो आफ्नै काठमाडौँमा हामी CDPTU मा, but we still purchased. Further, I wrote proposal to purchase 2 PCs in NAST. NAST ले 60,000 रुपैयाँ दियो, दुईटा PC लाई एक्चुअली त्यति बेला 65,000 पर्यो। Unfortunately, departments were not so generous to help me at that time. I approached one of my friends in USA and he provided his computers to run our job. पहिला molecular dynamics thesis हाम्रो नेपालमा यहाँ क्यारी अन गर्ने सुनिल थापा, he actually ran his job in USA. So त्यसरी पनि हामीले कम्प्युटेशनल फिजिक्स यहाँ केही न केही काम सुरु गरेका हौं। UGC provided faculty grants 2 लाख को भन्थ्यो, त्यति बेला ट्याक्स काटेर 1,70,000 दिएको थियो र it was sufficient to purchase 3टा PC, 2टा i5 र एउटा i7. We were very happy at that moment. They were considered very powerful at that time. It is just 1 decade. And I cannot actually share my happiness to have those 3 PCs at that time actually. An IBM server, 24 processors plus 2.3 kilowatt uninterrupted solar power system to power this and other machines were provided by TWAS in 2014. At that time, you can imagine we were having one generator also, load shedding was 16 hours, another server by ICQ13 and CDPTU alumni help गरेर 2017 मा आयो. At that time we had these 2 servers, one by TWAS and another by this ICQ13. Actually mostly 80% was from that one. And we had this uninterrupted power supply system from this solar one provided by TWAS. After then, UGC supported, UGC provided CRG, collaborative research grants in 2017. TWAS ले फेरि $32,000 दियो र 2टा गरी we have now actually 5 server machines in our lab. So at the meantime, computational physics course pani suru bhayo TU ma. It helped actually to enhance our knowledge in many front. So our MSc students write algorithm and solve the numerical methods problem nowadays, which we were not doing when we were students. It's actually advancement of time. They carry an MSc simulation study of Ising model, know how to get thermodynamic properties without partition function. Partition function ननिकालिकन केही पनि आउँदैन भन्ने हामी जुन स्टार्टको कन्सेप्ट छ त्यसलाई जुन मोन्टे कार्लोले ब्रेक गरेको त्यसको आइडिया युज गरेर our MSc and PhD students, PhD scholars, they carry on study of Ising model also. And a PhD student, all of them individually had to finish one project, no matter however small it is. That's going to be always computational physics project. However, there is enough room to improve, so we must work hard actually. Course work all these basic things, but we must enhance our quality in every front. Being limited resources, computing resources, our systems had to be small actually. There are two areas in which we are working. One is Hartree-Fock DFT, I mean quantum mechanical calculations. For this, we always consider very small systems, atoms to molecules, methane cathodes to 2D structures. Nowadays, our focus is on 2D structures and their defects. Another classical approach, molecular dynamic simulations. In this one, we have tackled some problems which are environmentally significant, ozone, oxygen, water like this, biologically significant, water, amino acids like this, physics significant, inert gases like neon, argon, krypton, daily life, our practical appliances like pharmaceuticals, amoxicillin, polymers, biopolymers, DNA, RNA, protein, their interactions. Our main current focus is protein-protein interactions, interaction of SARS-CoV-2 virus and human history. So because of that one, we are able to publish our articles in many international journals like Journal of Molecular Liquids. All these are MSc physics work. This Springer Journal, Journal of Molecular Modeling, and solid state communications. I mean, our problems are diverse, as I already mentioned. We carry on some molecular dynamics, Hartree-Fock DFT to work on superconductivity also. And we have published, CDP TU, you can see in IOP Publishing, Journal of Physics Communications and other journals, AIP, Physical Review B, like this. These are some impacts. And many MSc students carrying on computational physics as their career choice. So if you see, more than 80% of physicists are somehow involved with computational physics actually. Even hardcore physicists, experimental physicists should have at least one PhD or postdoc to help them to interpret their data in computational physics area. So up to now, 5 PhD finished and 5 are ongoing. And some of them are jointly supervised by our collaborators abroad. Last decade, we had very, very limited resources. So our systems were about just graphene like this. And now our current interests are heterostructures. This is because of improvement in our computing facilities. What we have now, you cannot compare with one PC about 2 decades, not 2 decades, about 1.5 decades ago, what we had, and we were very happy at that time. So our current interest is graphene and HBN heterostructure. We make heterostructure of graphene and HBN, hexagonal boron nitride, all these 2D materials, nanomaterials, and they are actually fascinating after Andre Geim and Novoselov proved that 2-dimensional material exists irrespective of the earlier theorem given by Landau. So we optimize these structures and study their electrical, magnetic, and transport properties. For these heterostructures, we produced one boron and one nitrogen defect system, and then we optimized and studied the electronic structures properties. In the case of 1B, I mean one boron defected system, in graphene parts, very small band gap opens 9.75 MeV. It's very small, and it shows semi-metallic behavior. Similarly, in case of nitrogen defect system, 33 milli electron volt like this band gap exists. And if you talk about magnetic properties of these heterostructure systems, both graphene and HBN do not possess magnetism. This is because spin distribution is symmetric, and if you make heterostructure, very small magnetism exists over there, and it's very small, means really small, 0.04 μV per cell. But this one nitrogen defect system makes it magnetic materials. So just by making pure system to defected system, you can create magnetism in your system. It's just because of reconfiguration of electronic structures, and you can understand such phenomena by using Horn's rule very easily, because you created this vacancy defects, and then there was deficiency of seven electrons in such systems. So it basically gives you rearrangement of electrons to this 0.97 μV per cell. In the side of transport properties, we have studied Seebeck coefficient for this graphene hexagonal boron nitride heterostructure systems, and this graphene possesses this Seebeck coefficient is 42 at 300 Kelvin, and this heterostructure possesses 8 at 300 Kelvin, and this 42 actually agrees with previously reported results also for monolayer system. And electrical conductivity, as you know, they are basically semiconducting system, this heterostructure system. There was a small band gap. So as you increase the temperature, electrical conductivity monotonically increases. That's what we can see. But in case of this one nitrogen defect system, first it decreases and then it starts increasing. It's because of curvature in the band structure. And if you look at the electronic contribution of thermal conductivity, this also keeps on increasing as expected, for these semiconducting systems. And thermoelectric power factor also keeps on increasing and decreasing. It always possesses one maxima. If you study this for long temperature range, you always see a maxima in this one. Because of two carriers, because of the competition in two carrier things. And this is one type of project what we are studying nowadays. And in this one, other type of materials are our future projects. They are going on actually Heusler type of materials. And another is, as I already mentioned, pharmaceuticals are our interest. We actually wanted to help pharmaceutical industry in our country to improve, in both fronts actually, to improve the effectiveness of already used drugs like amoxicillin. And our another goal is to screen different medicine for different diseases by using our computational skills. So actually, our current interest is this equation. Noyes and Whitney gave one equations in 1897. This LHS is dissolution rate. It's basically kinetic term. And this CS is solubility. thermodynamic term. And D is diffusion. This is transfer property. So these three things actually looks quite different. They are somehow connected by noise-Whitney equations. And to our best knowledge, actually, nobody tried to estimate this dmi dt or to study these equations coherently. So apart from obviously this noise and Whitney themselves, so we actually carried on simulation of this amoxicillin in water, because amoxicillin is dissolved in our body in water also, and its diffusion property is needed because that also determines the effectiveness of this drug in our body, and solubility also obviously that matters. So for this, we solved this Langevin equation and using this molecular dynamics tools. This is one of the main tools in our department nowadays. And Fixler gives this diffusion coefficient. That is one of the parameters of noise-Whitney equations, and that can be obtained from Einstein's relation for diffusion coefficient. That is for the finite system, because we use molecular dynamics, means of course finite systems, and we use this periodic boundary conditions in all the three directions. And from this mean square displacement and time curve, we can understand the diffusion coefficient. And for the mutual diffusion coefficient, we use these darkened relations. So molecular dynamics is actually the excellent tool. It is actually fascinating to understand, to carry on any experiment in statistical mechanics actually. Nowadays, anybody in StatMech, any guy or girls interested in StatMech, they carry on molecular simulations of molecular dynamics, Monte Carlo, Brownian dynamics, like this. So we also carried on simulation of that amoxicillin molecule in water at different temperatures. I mean, they are, even though the temperatures are different, they are actually close to our body temperature, because we don't want to go far from our body temperature. Our main goal is to understand what happens in body temperature. So this MST versus time, this gives diffusion coefficient similarly at different temperatures for different sizes also. And here we present this diffusion coefficient of amoxicillin and water and mutual one. If you compare water, diffusion coefficient of water estimated in our lab with previously reported experimental results, they agree within 8.5%. As expected, the diffusion coefficient obviously increases with increasing temperature. And we wanted to understand this activation energy for diffusion of amoxicillin. And for this, we assumed that our system follows RNS behavior. And we studied this diffusion coefficient as a function of temperature, as already mentioned. And we fitted this RNS behavior. From that one, we estimated this activation energy for diffusion of amoxicillin, which turns out to be 0.017 kilojoule per mole. And for water, it turns out to be 15. And experimental value is 17, which agrees with our results within around 12%. And to get this free energy of solvation, this solubility, we use free energy perturbation method and thermodynamic integration method. Actually, there are quite a few methods nowadays developed, well-developed methods, and they are used widely. They are widely used to get this solubility, solvation free energy and solubility. Now, we use these two methods. This free energy perturbation methods is actually based on configuration integration. Actually, what happens to get this free energy? You need to have this potential energy term, which depends upon configuration of two state, the thermodynamic state 1 and state B, and another is kinetic energy term that actually cancels out if you want to take differences in A and B state. And another thing is that that's very easy to calculate because of this e raised to the power minus p square by twice m terms. That's what you can calculate it analytically also. So main culprit is getting this configuration integration is really tough things. And if your system, if your states are overlapping like this, it's you are very lucky. Most of the time, you are not lucky because your initial state A and final state B, for which you are interested in free energy calculations, then they do not overlap like this initial state A and final state B. Then you need to create some non-physical states. That's what we do in free energy perturbation. We start from initial state A, we perturb the system and reach up to this one, and again perturb to this, and so on, finally to final state B. Finally, you know, this free energy is state function. I mean, very nice thermodynamic function. This does not depend upon these all these on non-physical intermediate states, and you can just get this difference like this given by this equation. And another method is thermodynamic integration method. In thermodynamic integration method, what you do, we take certain parameters, say lambda, and we define it between 0 and 1, state 0 and 1. 0 and 1 are the system is already dissolved in, your solute is already dissolved in this solvent, and another is non-dissolved. So, but here again, you need to consider many thermodynamic states. You cannot simply run your molecular simulation at 0 and 1 to get your free energy differences, because again, there needs to be this process has to be changed very slowly. That's what we did. And we estimated this free energy of solvation of amoxicillin in two different solvents. One is water and ethanol. In water, you see, if you are interested to study water, it's really a very interesting topics, because water is one of the most studied system, because biologists study, mathematician, chemist, physicist, everybody study, but still it's so many anomalous properties could not be understood. So there are too many models for water. Out of them, for this purpose, we chose TIP 3P and SPC model. And in those two models, our these solvation free energy are not much different. Another is another solvent we chose is ethanol, because we wanted to understand whether this, even though this is widely accepted fact that amoxicillin may not dissolve in ethanol like that does in water, but still quantitative data does not exist in literature. So we wanted to understand it quantitatively also. If you compare this data with I mean, the free energy of solvation of amoxicillin in water and ethanol, they are clearly different, about 100 kilojoule per mole. And to get feelings about whether our data are close enough to similar systems, we compared Schweiter ionic molecule like this glutamic acid, and here we found this agreeing within about 12%. And another way to check is Born equation also. We compared our data from Born equation also, and it gave about 547 kilojoule per mole. So which are comparable with our two different water models. And to understand this higher solvation free energy, we checked this how this hydrogen bond, number of hydrogen bond vary in two different solvents, this TIP 3P SPC water and ethanol. I mean, this upper one is for water, and this lower one curve almost about 15 hydrogen bond is for ethanol. So ethanol has lower free energy of solvation that can be understood from this hydrogen bond also, and that can be further understood by studying this solvent accessible surface area SASA. SASA also turns out to be significantly less than these both of these two models. So another this is the way how we are trying to understand already existing medicines, drugs, to improve their efficiency. So another system what we are studying is DNA protein complex. So in DNA protein complex, actually, we wanted to understand this DNA damage repair. And this DNA and protein interact, and there are many different ways how DNA can damage, and methylation is one of the ways how our DNA damages in our body. And our interest was to understand whether it can repair itself. For this, we wanted to understand this. We wanted to understand whether this demethylation of DNA can happen in our body at the given temperature. I mean, at the given environment, ambient condition like this. So for this, what we did, we formed methylated guanine, I mean DNA system, and one methylated protein, and methylated protein, and then one methylated DNA system, and another is transient state system in which there will be a covalent bond between sulfur and carbon. So for this, we wanted to understand this free energy differences between complex 1 and 3rd, so that we carried out our this umbrella sampling, so-called umbrella sampling. As I already mentioned, there are many different ways to study this free energy of your system. For such systems, such complex system, you cannot use neither this free energy perturbation nor this thermodynamic integration. You need to go for techniques like umbrella sampling. From umbrella sampling, we estimated thus the difference in free energy. Actually, these are difference delta. Yes, they are difference in free energy differences. Pre-methyl transfer. I mean, when your DNA was methylated, that time's curve is guanine. I mean, this blue one, and this red one represents this methylation of protein, and the difference turns out to be 1.0 kilocalorie per mole, which can easily be overcome at a room temperature, I mean our body temperature. So this damage repair happens easily. And today's focus, actually, I wanted to focus on protein-protein interactions, binding of SARS-CoV-2 and SARS-CoV spike protein with human S2 receptor, and then other different variants of SARS-CoV-2, because this is going to be, I mean, SARS-CoV-2 is going to be here for some time, it looks so. So what we wanted to study, SARS-CoV-2 virus uses human S2 receptor to enter target cells. So entry process is mediated by the spikes glycoprotein in SARS-CoV-2. So we are investigating major amino acid residues and interactions at the binding interface between the viruses RBD and host receptor. Free energy difference estimation by using umbrella sampling for these two. Actually, that's what we carried out almost 2 years back when this SARS-CoV-2 was there, and we were in lockdown. This project was going on in our lab, and we carried out this study, SARS-CoV and SARS-CoV-2 spike protein binding with our receptor, human receptor. So for this, as there is limited time, I would like to skip. Our findings actually showed first time that there are three main regions of hydrogen bonding or binding sites in this spike protein and human S2. This right side one is human S2, our enzyme, our protein, our body's protein, and this blue one, sky blue one is spike protein of this SARS-CoV-2, and they bind here in three different regions. So the three different regions, they are actually for SARS-CoV also. Then the question comes, why SARS-CoV-2 is so severe, and why this SARS-CoV, I mean, SARS-CoV we did not feel here in Nepal or any other places except in China. So we wanted to understand this region from our molecular simulations calculations. And then we try to find out these different hydrogen bonds in those three different regions. And this figure shows the hydrogen bond occupancy for different residues in SARS-CoV-2 and human S2 interface. And from in this third region comes much more hydrogen bond. I mean, that remains much more intact actually. Similarly, for the SARS-CoV also there are similar type of regions. However, if you see, there are less number of hydrogen bonds in all the three regions, and number of hydrogen bonds are less, and hydrogen bond occupancy is also less in comparison to SARS-CoV-2. So, so this somehow explains why SARS-CoV is not so severe like SARS-CoV-2, or why SARS-CoV-2 is severe than much more severe than SARS-CoV. So after then, we compare the hydrogen bonds into complexes also. So obviously your blue one is for SARS-CoV-2, the red one SARS-CoV-2. Red one को यहाँ fluctuation by पनि total मा number of hydrogen
Good.
हेलो के भयो मैले सुनेन
होइन सरको साउन्ड सुन्दैन
सर म्युट हुनुभयो जस्तो
म्युट होइन होला
सरको त्यहाँ के भयो
लाइन गयो कि सरकोमा
बत्ती गयो है मेरोमा गएर भर्खर आएको थियो
सर उता लेफ्ट ग्रुपमै हुनुहुन्छ
नेट प्रब्लम भयो सरको
नेट प्रब्लम भयो सर उनी गयो
नारायण सर
हजुर
सुनेको छ
ल ओके थ्यांक यू सो मच आई एम सरी मैले शेयर गरेको देखिएको छ अहिले
आइसकेको छैन सर शेयरिङ हुँदैछ यहाँ देख्नुहोस्
ओके भन्नुहोस् है मैले भिडियो अफ गर्छु अनि ओके हेलो
सुन्या सर
साउन्ड क्लियर छ
क्लियर छ
ओके गुड एम आई ऑडिबल एम आई विजिबल
audible is okay sir no need to visible
देखिएको छ
screen is coming now
स्लाइड आएन
आइसकेपछि भन्नुहोस् है क्लियर छ देखियो अहिले
यस सर
पर्फेक्ट सर पर्फेक्ट
yes okay
भिजिबल छैन त्यहाँ मेरो स्लाइड आएको छैन
आएको सर
आयो फाइन
आयो
सर
ओके सो हामीले अघि यही कम्पेरिजन अफ हाइड्रोजन बोन्ड्स इन दुईटा डिफरेंट कम्प्लेक्सेस SARS-CoV-2 र ओके SARS-CoV-2 र अनि SARS-CoV को ह्युमन S2 सँग चाहिँ कस्तो टाइपको बाइन्डिङ हुन्छ भन्ने कुरा हामीले हेर्दै थियौं अनि हामीले नन बोन्डेड इन्टरेक्सन्सहरु पनि त्यसमा हेर्यौं स्टडी गर्यौं एक्चुअली नन बोन्डेड इन्ट्रेक्सन्सहरुमा पनि हामीले हेर्यौं भनेदेखि के भेटिन्छ भन्दाखेरि COP2 को मच मोर स्ट्रङ्गर देन SARS CoV ओन्ली छ अनि त्यसमा इलेक्ट्रोस्ट्याटिक्स र भेन डर वाल्स दुईटै नै त्यस्तो देखिन्छ। पछि हामीले बाइन्डिङ फ्री एनर्जी चाहिँ डिफरेन्स हेर्यौं अम्ब्रेला स्याम्पलिङबाट। त्यो अम्ब्रेला स्याम्पलिङबाट हेर्दाखेरि दुईटाको फ्री एनर्जी डिफरेन्स 1.91 किलो क्यालोरी पर मोल छ। यसको मतलब यसले हामीलाई के बुझ्न हेल्प गर्यो भन्दाखेरि SARS CoV-2 किन सिभियर भइरहेको छ भन्ने कुरा बुझ्न हेल्प गर्यो। अहिले आएर के छ भन्दाखेरि देयर आर डिफरेन्ट भेरिएन्ट्स। सो डिफरेन्ट भेरिएन्ट्स को बाइन्डिङ इन्टरेक्सन बाइन्डिङ मेकानिजम हाम्रो बडी को ह्युमन S2 सँग कस्तो छ भन्ने कुरा दिस प्रोजेक्ट इज गोइङ अन नाउ वी हैव completed somehow preliminary results about 4 different types of different variants। यो जुन SARS CoV-2 को डिफरेन्ट भेरिएन्ट्स थियो डेल्टा बीटा ओमिक्रोन म्यू ती चारवटा को र वाइल्ड टाइप भनेको सबभन्दा पहिला आएको जुन म्युटेसन नभएको भेरिएन्ट्स हो त्यसको चाहिँ हामीले स्टडी त्यसको नम्बर अफ हाइड्रोजन बोन्ड्स हेर्यौं भनेदेखि यसमा क्लियरली डेल्टा को बढी देखिन्छ। यसमा भन्दा यसमा बढी क्लियर देखिएला। यसमा मैले हामीले रनिङ एभरेज अफ हाइड्रोजन बोन्ड्स हो। यसमा यो कलर को चाहिँ डेल्टा भेरिएन्ट को हामीले हेर्यौं भनेदेखि चाहिँ इट्स हाईएस्ट वान इन कम्पेरिजन टु एनी अदर्स वान र वाइल्ड टाइप डेल्टा भेरिएन्ट्स पछि वाइल्ड टाइपकै बढी वाइल्ड भेरिएन्टको बढी र त्यसपछि अरु तीनटाको चाहिँ नगण्य छ जुन चाहिँ हामी डिफरेन्स नगर्ने छ जुन चाहिँ हाम्रो सिभियरिटीबाट नि बुझ्न सक्छौं र ओमिक्रोन चाहिँ के थियो भन्दा त्यसको ट्रान्समिसिबिलिटी बढी थियो तर सिभियरिटी थिएन। जुन कुरा चाहिँ हाम्रो यसले नम्बर अफ हाइड्रोजन बोन्ड्स कम बनाएको कुराबाट बुझ्न सकिन्छ ट्रान्समिसिबिलिटी होइन कि सिभियरिटी कम भएको कुराकानी। र त्यस्तै गरी हाइड्रोजन बोन्ड्स इन डिफरेन्ट भेरिएन्ट्स को अकुपेन्सी हेर्यौं भनेदेखि पनि हामीले चाहिँ यो चारवटा पाँचवटा भेरिएन्ट्स को हेर्यौं भनेदेखि सबभन्दा बढी डेल्टा भेरिएन्ट्स चाहिँ हामीले भेटाउँछौं। त्यस्तै गरेर सल्ट ब्रिज इन्टरेक्सन हेर्यौं भनेदेखि पनि डेल्टा को लङ टाइम र हाईएस्ट छ भनेदेखि म्यू को डिस्टेन्स चाहिँ बढी छ को मतलब के हो भन्दाखेरि सल्ट ब्रिजमा अलिकति फरक तरिकाले प्रेजेन्ट गरेको हुन्छ। सल्ट यो म्यू को चाहिँ डिस्टेन्स टाढा छ भनेपछि इट्स मच मोर विकर देन अदर्स भन्ने कुरा हो। यसमा वाइल्ड र म्यू डेल्टा हामीले कम्पेयर गरेका थियौं। त्यस्तै गरी नन बोन्डेड इन्टरेक्सन्समा भेन डर वाल्स इन्टरेक्सन्स इन डिफरेन्ट भेरिएन्ट्स हेरौं हामीहरु। भेन डर वाल्स इन्टरेक्सन्समा हामीले रनिङ एभरेज अफ भेन डर वाल्स इन्टरेक्सन्स निकाल्यौं भने यो भेन डर वाल्स इन्टरेक्सन ओमिक्रोन को बढी छ। ओमिक्रोन को बढी छ भन्नाले विकली बाइन्डिङ हुने इन्टरेक्सन जुन छ अरुको भन्दा बढी ओमिक्रोनमा रहेछ। त्यसपछि चाहिँ म्यू को छ म्यू भेरिएन्ट्स को छ र यो डेल्टा को यो भेन डर वाल्स इन्टरेक्सन्स त्यति धेरै शार्प छैन। त्यस्तै गरी हामीले इलेक्ट्रोस्ट्याटिक्स इन्टरेक्सन हेर्यौं र इलेक्ट्रोस्ट्याटिक इन्टरेक्सन यो पाँचवटा को कम्पेयर गर्दाखेरि रनिङ एभरेज अफ इलेक्ट्रोस्ट्याटिक्स इन्टरेक्सन हेर्दाखेरि यो बीटा को सबभन्दा विक छ र सबभन्दा स्ट्रङ चाहिँ यो डेल्टा को छ। अरु तीनवटा को चाहिँ बीचमै पर्छ तिनीहरुको बीचमै पर्छ अथवा अलमोस्ट इक्वल छ। In this way we are trying to understand यो सिभियरिटी यो डिफरेन्ट भेरिएन्ट्स को जुन छ हामीले आफूले जानेको बुझेको फिजिक्स युज गरेर व्हाट वी आर ट्राइङ टु अन्डरस्ट्यान्ड सिभियरिटी कुनमा बढी किन हुन्छ कम किन हुन्छ यो कुराकानी बुझ्न हेल्प हुने रहेछ हाम्रो मोलिकुलर डायनामिक्स सिमुलेसनबाट पनि। र इलेक्ट्रोस्ट्याटिक्स इन्टरेक्सन डिफरेन्ट भेरिएन्ट्समा हामीले हेर्यौं भनेदेखि यो फाइनल टेबलमा चाहिँ हामीले डिफरेन्ट भेरिएन्ट्सहरुको डिफरेन्ट इन्टरेक्सन्स एभरेजमा प्रेजेन्ट गरेको। डेल्टा को नम्बर अफ हाइड्रोजन बोन्ड्स अलमोस्ट 8 छ भने सबभन्दा कम ओमिक्रोन को छ 5 छ। सबभन्दा कम सिभियर पनि ओमिक्रोन नै थियो हामी सबैलाई थाहा छ। यो नम्बर अफ हाइड्रोजन बोन्ड्सबाट पनि केही कुरा क्लु आउने रहेछ। डेल्टा को नन बोन्डेड चाहिँ -291 छ मच मोर स्ट्रङ्गर छ भने सबभन्दा कम चाहिँ बीटा को छ नन बोन्डेड इन्टरेक्सन्स -144 जति छ। In this way, we are trying to understand the binding mechanism of different variants with our human S2 protein. This project is still going on, and our MSc students are, many MSc students are involved in this project. And to understand this project, we have recently obtained 48 lakh grants from Tribhuvan University Research Division Rector Office. So finally comes these conclusions. We presented bird's eye view of what we are doing. Graphene HBN is a good candidate for thermoelectric properties. Methylated cysteine has free energy of 1.3 kilocalorie per mole more than methyl guanine. Demethylation of DNA is possible by AGT protein. Important non-bonded interactions, hydrogen bond, salt bridges, electrostatics, and van der Waals interactions were studied for this DNA AGT. Similarly, all important interactions were relatively stronger in case of SARS-CoV-2. SARS-CoV-2 CTD binds to S2 with greater affinity than that of SARS-CoV RBD. Delta variant looks more dangerous than any others from this analysis of this binding mechanism. Finally, the acknowledgement goes to ICTP, TWAS, UGC, CDPTU, Professor Misra, Jha sir, Gurung sir, MMS sir, SPB, and all other professors. ICTP, Professor Iskandalo Ali, FIU, Professor Prem Chapagai Tiwari from Georgetown University, USA, Professor Nair from IITK, from GNCSR Narasimhan, Professor Narasimhan, from IIT KGP, Professor Tarafdar, from University of Maryland, McCarrell, ISER Pune Ghosh and Singh, CIFRF Professor Sinway, from SNB and CBS and Suni Albani led Professors Mukherjee and Das, who actually helped to develop this computational physics in Nepal. All our PhD scholars, Dr. Kafle, Dr. Pantha, Dr. Laimchane, Dr. Khanal, Dr. Koirala, Pokhrel, Thapa, Khatri, Mr. Harikrishna Neupane, Julan Paudel, etc. And MSc students who carried out, who studied these different variants of this SARS-CoV-2, Lokendra Dhami, Lalit Dhami, Asmita Shah, Praveen Dahal, and more than 100 other students who helped to develop this area. Thank you so much. If you have any questions, I will be very happy to answer. Unfortunately, there was some technical problem. I apologize for all this. Thank you so much. I hope you understand the problem with these technical things. Thank you.
Narayan sir, namaskar. Good morning,
Yes,
Leknath Bhusal.
Okay, namaskar, namaskar. Oh, Bhusal sir.
Very good. Very Kusilal, congratulations setting up the stone for computational physics in Nepal. It's very impressive.
Thank you.
एउटा question र एउटा comment छ है. So the question तपाईँले the data देखाउनु भएको थियो नि versus time.
Yes.
In that data, why it's fluctuating with time? Time बाट किन तलमाथि गइरहेछ?
ओके, टाइम सँग चाहिँ हाम्रो टाइम अनुसार के हुन्छ भन्दाखेरि डाटा फ्लक्चुएसन हुन्छ. किन हुन्छ भन्दाखेरि हामीले फेज स्पेसको डिफरेन्ट पोइन्टहरु स्याम्पलिङ गरेका छौं र फेज स्पेसको एनफ सिस्टम भइसक्यो भनेदेखि इन्समल एभरेज र टाइम एभरेज इक्वल हुने हो र त्यो भएर हामीले यसको एभरेज भ्यालुहरु प्रेजेन्ट गरेका छौं लास्टमा. यो भ्यालुहरु एभरेज हो एक्चुअली सबैको लिएर.
The time of the hydrogen impact of hydrogen bond time मा किन डिपेन्ड गर्छ त भन्ने कुरा.
डिफरेन्ट फेज पोइन्टमा गएपछि म्याक्रोस्कोपिक प्रपर्टिजहरु त भेरी गर्ने भयो नि.
Oh, I see. Okay. So time is not the computational time. It is the time when molecules are moving around.
Exactly. This is not CPU time. This is real time, real dynamics. Yeah.
Okay. So our question, I mean, computational physics. I mean, it's very accessible, but the problem is the resources. The computational resource is very expensive, and keep updating is very expensive. So have you ever thought of using cloud computation like from Amazon? Because you can rent a time for very, very powerful computer server. And it's not.
Yes, right now we are focusing our attention to strengthen something in our lab also. Of course, we are thinking and studying how we can use this cloud computing also, Leknath sir.
क्लाउड कम्प्युटिङमा के भयो भने अब कम्प्युटेसनल त भेरी कम्प्लेक्स अब एक वर्ष लाग्ने calculation in small server you can do in one day, right?
Yeah.
So and to build a computing server to finish 1 year job in 1 year,
Yes.
very expensive and very, very time consuming. So
Yeah.
I think it's always good to think renting. It's like renting a room, right?
हो रेन्टिङ नै हो त्यो क्लियरली रेन्टिङ हो तर अब नेपालबाट कसरी एसेस गर्ने त्यसको पैसा कसरी म्यानेज गर्ने त्यसको लागि कसरी प्रोजेक्ट लेखेर बुझाउने all these things actually I am thinking about it but clearly way out भइसकेको छैन होमवर्क गर्दै छौं भन्दा हुन्छ
So actually a problem is just the funding,
yes,
right?
Yes,
project
yes.
I mean so we can talk about how if there is a project and how to fund it. There are different ways to fund for like 1 hour or 1 day of time in server.
Yes,
we should think about that. Anyway, that's my comment and question. Thanks.
No,
Congratulations.
Thank you so much, Vishal sir. Thank you.
कृष्ण राणा मगर हात उठाउनु भएको रहेछ क्वेसन गरौँ प्लिज
हजुर सर थ्याङ्क यू फर द नाइस प्रेजेन्टेसन म नेपालीबाटै जान्छु है सर
हस् प्लिज
सर यो हजुरले 27 नम्बर स्लाइडमा हुनसक्छ त्यो फार्मास्युटिकल्सलाई पनि हेल्प हुने तरिकाले हामीले गर्दैछौँ भनेर भन्नुभयो नि होइन एमोक्सिलिनको इक्जाम्पल दिनुभएको थियो
यस
हो त्यसमा सर यो कसरी चाहिँ इफेक्टिभनेस बढाउने सर मैले अलिक बुझिनँ होला सायद
यो
स्ट्रक्चर नै चेन्ज लिएर आउने हो कि जस्तै बोन्ड लेन्थहरु घटाउने हो कि
इफेक्टिभनेस केमा पनि डिपेन्ड गर्छ भन्दाखेरि यो डिसोलुसन रेट र इन्टेस्टाइनल पर्मिएबिलिटीमा डिपेन्ड गर्छ है इन्टेस्टाइनल पर्मिएबिलिटीमा डिपेन्ड गर्ने भएकोले त्यसलाई के गरी बढाउने फिजिकल उपायहरू हुन्छन् फिजिकल प्यारामिटरले इफेक्ट गर्छन् त्यो कुरा स्टडी गर्यौं भनेदेखि त सेम डोजको मेडिसिनले पनि हामीलाई हेल्पफुल हुने भयो नि
भयो सर त्यसमा
त्यो हो
तर मेरो चाहिँ अलिकति कन्सर्न चाहिँ कस्तो त भन्दा सर जस्तै अब एक्सटर्नल प्यारामिटर्स नै किन अब त्यो हजुरले भन्नुभएको जस्तै त्यो यसको स्ट्रक्चरल चेन्ज त लिएर आउने कुरा भएन हैन हजुरले भन्नुभएको छ
स्ट्रक्चरल चेन्ज होइन यो मेडिसिनको इफेक्टिभनेस डिसोल्युसन रेट इन्टेस्टाइनल पर्मिएबिलिटीमा डिपेन्ड गर्छ
हजुर
त्यो कुरा हामीले क्लियरली बुझ्यौं भनेदेखि जुन मेडिसिन हामी युज गर्छौं त्यो फेनोमेना हाम्रो बडीको अरु कुन प्यारामिटरसँग डिपेन्ड गर्छ भन्ने कुराहरुसँग बुझ्यौं भनेदेखि अभियसली यसको इफेक्टिभनेस बढाउनमा हेल्प हुन्छ
त्यसैले सर यस्तो अब त्यसको लागि त हामीले यो जस्तै अब एक्सटर्नल फ्याक्टर्सहरुमा त अब एउटा त हजुरले टेम्परेचरको त रिलेसनशिप नै देखाइसक्नु भएको छ अब टेम्परेचर प्रेसरको कुराहरु आउँछ होला हैन सर अब त्यसलाई
चाहिँ टेम्परेचर प्रेसर हैन कृष्णजी हाम्रो यसमा के हुन्छ भन्दा हाम्रो बडी सँगै भएको कुराहरु लिने हेर्ने हो इन्टेस्टाइनल पर्मिएबिलिटी भने नि मैले त्यो प्यारामिटर बुझ्नु पर्छ हामीले
कृष्णजी अनम्युट गर्नु
यसको प्यारामिटरहरु बुझेर चाहिँ हामीले त्यही अनुसारको डोजहरुको लागि रिफर थ्यांक यू सर थ्यांक यू सर
अरु कुनै क्वेशन छ प्लिज
सर
हजुर
नमस्कार सर
नमस्कार
सर त्यो जुन त्यो भाइरसहरु लेखिन्छ नि सर त्यहाँ जस्तो ओम्निक्रोनहरु लेख्नु भएको छ नि 4-5 वटा भाइरसहरु
हजुर हजुर
त्यो के कसरी छुटाउन सकिन्छ सर यसमा
त्यसको म्युटेसन कसरी भएको छ भनेर भन्नु म्युटेसनको आधारमा छुट्याएको हो
ए हजुर ओके सर
सर सर नमस्कार सर नारायण सर
नमस्कार
धेरै राम्रो प्रेजेन्टेसन सरको लाग्यो मैले एउटा कुरा सर बुझ्न खोजेको जस्तै अब सार्स कोभिड-2 सार्सहरुको सरले दिएर विभिन्न भेरिएन्टहरुको जुन कुरा गर्नुभयो हाइड्रोजन बन्डसँग हाइड्रोजन बन्ड को त्यो जसमा बढी थियो त्यो बढी भन्न देखेको थियो अलिक खतरा देखेको थियो हैन सर
हाइड्रोजन बन्ड हैन एउटा छ हाइड्रोजन बन्ड एउटा प्यारामिटर हो
एउटा फ्याक्टर हाइड्रोजन बन्ड छ फ्याक्टर छ हाइड्रोजन बन्ड चाहिँ देखिएको भनेपछि त्यो हाइड्रोजनको त्यो सिरियसनेससँग के इफेक्ट छ यता त हामीले यो हाइड्रोजन बन्ड जसमा देखियो त्यो बढी इफेक्ट सिरियस देखियो सिभियर देखियो त्यो हामीले गर्यौं
हैन त्यो त यस्तो भयो नि
हाइड्रोजनको कारणले किन भएको होला त्यो खालको स्टडी पनि सरले केही गर्नु भएको छ कि
होइन,
त्यतातिर?
यो त अभियस छ बब्लु सर, किन भन्दा हाइड्रोजन बोन्डको नम्बर र स्ट्रेन्थ बढ्यो भनेदेखि रिलेटिभली त्यो भाइरस आएर हाम्रो बडीमा बढी फोर्ससँग मान्दियो, बढी इनर्जीसँग टाँसियो।
ए हजुर हजुर सर।
हामीले त अभियसली फिजिक्स भएको हुनाले इनर्जी प्यारामिटरसँग हेरेको।
हजुर सर, ओके सर, थ्याङ्क यू सर।
सर
एकदम साह्रै राम्रो प्रेजेन्टेसन सर। सर साह्रै डेडिकेटेड भएर काम गर्नुभएको छ। किप डुइङ।
थ्याङ्क यू।
ओके, अरू केही छ क्वेसन अरूको? तर म एउटा सानो सोध्नु मन लाग्छ।
हजुर
सर, त्यो एमोक्सिसिलिनमा त्यसको सरले 12% मा एक्सेप्टेबल छ भनेर भन्नुभएको थियो जस्तो लाग्यो।
होइन, एक्सेप्टेबल भनिन, त्यो पुरानो डाटासँग कम्पेयर गर्दा होला। पुरानोसँग कम्पेयर गर्दाखेरि चाहिँ 12% चाहिँ आएको छ।
भनेको कसको राम्रो भयो त भन्ने कुरा?
होइन, जस्तो यो डिफ्युजन चाहिँ 8.5% छ। यहाँ राम्रोको कुरा कहाँ आयो र 12% त? 12% राम्रोमा भन्नेमा आएको छैन।
मैले त्यो बुझेन सर, त्यो के भन्न
खोजे? यो हो, यसमा हो
यहाँ हो। हजुर सर,
यसमा त यस्तो हामीले चाहिँ के गर्यौँ भन्दा एमोक्सिसिलिनको फ्री एनर्जी अफ सल्भेसन इस्टिमेट गर्यौँ वाटरमा र इथानोलमा। अनि वाटरमा गरेको हाम्रो -500 समथिङ आएको छ। डिफ्रेन्ट मोडलमा डिफ्रेन्ट मेथडले -530 को रेन्जमा आएको छ होइन। अब यो चाहिँ एक्सपेरिमेन्ट कुनै पनि भेटिएन यस्तो टाइपको। केही पनि नभेटिएपछि हामीले केसँग कम्पेयर गर्यौँ भन्दा ग्लुटामिक एसिडको फ्री एनर्जी अफ सल्भेसन एक्सपेरिमेन्टली मेजर गरेको रहेछन्। ग्लुटामिक एसिड पनि ट्वाइटर आयोनिक, अनि हाम्रो यो एमोक्सिसिलिन पनि ट्वाइटर आयोनिक। त्यो भएर दुईटैको फ्री एनर्जी सल्भेसन कम्पेयरेबल हुन्छ। त्यो कारणले गर्दा हामीले ग्लुटामिक एसिडसँग कम्पेयर गरेको, जुन चाहिँ 12.3% छ भनेर भन्न खोजेको। यसमा
12% हाम्रो आएको डाटा उसको 12% हो भन्ने त होइन।
होइन, सिस्टम नै डिफ्रेन्ट हुन् तर सिमिलर सिस्टम। सिमिलरिटी के भयो भन्दा ट्वाइटर आयोनिक फर्मका भयो दुईटै, एमोक्सिसिलिन र ग्लुटामिक एसिड। त्यो भएर ट्वाइटर आयोनिकसँगै फ्री एनर्जी अफ सल्भेसन कम्पेयरेबल हुन्छ। त्यो भएर हामीले कम्पेयर गरेको मात्रै हो।
12% ले डिफर भयो भन्न खोज्यो हामीले।
हो, हाम्रो जुन फ्री एनर्जी अफ सल्भेसन छ एमोक्सिसिलिनको र ग्लुटामिक एसिडको वाटरमा 12% भेरी गर्यो भनेको, डिफ्रेन्ट छ भनेको।
ओके, कुन चाहिँ सुटेबल चाहिँ भन्न पाइएन।
होइन, सुटेबल भन्ने त कुरै गरेको होइन, कुनै क्लेम पनि होइन यसमा त।
ओके सर, ओके, आई अन्डरस्ट्यान्ड।
वाटर र इथानोलमा वाटरमा सुटेबल भन्ने क्लेम हो हाम्रोबाट, टेबलबाट है। त्यसले चाहिँ जस्तो इथानोल कन्ज्युम गरेको मान्छेलाई एमोक्सिसिलिनले किन कम इफेक्ट गर्छ भन्ने कुराको बुझ्न मद्दत गर्यो नि फेरि यसले। यो वाइडली एक्सेप्टेड कुरा हो, तर यसरी क्वान्टिटेटिभ नम्बरहरू हाम्रो पेपरहरूमा देखिन्न, त्यो निकालेको हामीले यसमा एक्चुअली।
थ्याङ्क यू। अरू कोही हुनुहुन्छ क्वेसन सोध्नु?
मलिक सर, मैले आफ्नो पालो क्वेसन सोधिसकेँ। एउटा अरू सोध्न टाइम छ भने?
एकदम।
नारायण सर,
हजुर।
सो तपाईँले अर्ग्यानिक मात्रै कुरा गर्नुभयो, इनअर्ग्यानिक मटेरियलमा कुनै एक्टिभिटी छ कि? सेमिकन्डक्टर, म त एक्सपेरिमेन्टल फिजिसिस्ट हो। दिस इज टु कम्प्लेक्स फर मी, आई डोन्ट अन्डरस्ट्यान्ड many things. So सेमिकन्डक्टर और इनअर्ग्यानिक मटेरियलमा कुनै एक्टिभिटी छ तपाईँको?
होइन, सेमिकन्डक्टर तिनीहरूमा नि हाम्रो एक्टिभिटी छ। आज अभियसली सबै कुरा समेट्न गाह्रो हुने हो, गाह्रो हुने नै भयो। त्यसमा पनि अझै धेरै समेट्न खोजिएछ। यसो फिलिङ्स कम्तीमा पिएचडी को अहिले अनगोइङ प्रोजेक्ट्सहरूको फिलिङ्स दिउँ भन्दाखेरि अझै धेरै भएछ होइन। म बिस्तारै ती सबै कुराहरू सेयर गर्ने सोसाइटीले अनुमति दियो अथवा पाइयो टाइम भने स्लोली गर्दै जान्छु ती कुराहरू। त्यो पनि छ लेख्न सर, हामी डिस्कस गरौँला।
ठिक छ, जान्न खोजेको कि फोकस इन जनरल अरूतिर यो कम्प्युटर फिजिक्स त अब जेमा पनि युज गर्न पाइयो, अब फोकस कतातिर छ भन्ने। ओके, थ्याङ्क यू।
थ्याङ्क यू विशाल सर। करण जी प्लिज।
सर थ्याङ्क यू फर नाइस प्रेजेन्टेसन। मलाई त्यहाँ सिब्याक कोएफिसिएन्ट र पावर फ्याक्टर पनि देखेँ होइन। अनि हाम्रो सिडिपीमा त्यो पनि क्याल्कुलेट गरिन्छ कि कस्तो हो?
गर्छौँ, यो हामीले गरेको त हो नि।
अनि सर त्यसको भ्यालिडिटी चाहिँ कसरी चेक गरिन्छ?
यो चाहिँ अब अलिकति उ छ, हामीले एक्सपेरिमेन्ट पनि गर्दैछौँ। अब यो आइसर पुणे देखाएको थिएँ नि मैले, त्यहाँ मिलेर एक्सपेरिमेन्ट पनि गर्दैछौँ। यसको भ्यालिडिटी भन्ने कुरा त यो अभियसली क्याल्कुलेसन गरेको कुराहरू एक्सपेरिमेन्टसँग कम्पेयर गरेर त्यस्तै टाइपको सिस्टमसँग कम्पेयर गरेर भ्यालिडिटी गर्ने हो। भ्यालिडिटी हामीले त्यसरी नै गरेका छौँ अहिलेसम्म। हामीले आफैले एक्सपेरिमेन्ट गरेका छैनौँ, तर गर्दैछौँ। अब निकट भविष्यमै गर्छौँ। विदिन 1 इयर हामी एक्सपेरिमेन्टल रिजल्ट्स यस्तो देखाउन सक्छौँ तपाईँहरूलाई भन्ने आश छ मलाई।
ग्रेट सर। थ्याङ्क यू करणजी फर क्वेसन्स। अरू कोही हुनुहुन्छ? हुन्छ भने अब हामी इन्ड गरौँ, हाम्रो टाइम पनि धेरै एक्सिड भइसक्यो।
टाइम त अनफर्चुनेटली टेक्निकल कुराले पनि हो है मलिक सर।
हजुर एकदम
8:30 भएछ।
लेखनाथ सर, could you please conclude the session?
Okay. Thanks for your nice presentation, Professor Dr. Narayan sir. सरले साह्रै राम्रो प्रेजेन्टेसन दिनुभयो र यो चाहिँ टाइम कन्स्ट्रेन्ट अथवा चाहिँ त्यो अलिकति टेक्निकल्ली अलिकति प्रब्लम भए पनि साह्रै अब यो हामी त यस्तोसँग हरायौँ कि सुन्दा चाहिँ अझै सुनौँ जस्तो लागिरहेको थियो। समयले अलिकति हामीलाई अलिकति पनि गरिसक्यो र आज श्रीकृष्ण जन्माष्टमी भएको हुनाले सबै यस अवसरमा सबैलाई शुभकामना दिन पनि चाहन्छु मेरो तर्फबाट र फिजिकल सोसाइटीको तर्फबाट पनि। र उहाँको यो जुन निरन्तरता छ, यो निरन्तरता अगाडि बढ्ने नै छ र उहाँ आफै हिस्ट्री हो भनेर अगाडि हाम्रो मल्लिक सरले भनिसक्नुभयो। र उहाँले यो कम्पिटिसनल चाहिँ एउटा एक प्रकारको यो सिडो अथवा चाहिँ भर्चुअल एक्सपेरिमेन्ट हो र उहाँले अब रियलै एक्सपेरिमेन्ट गर्न खोज्नु भएको छ। यसले हामीलाई साँच्चै नै एकदमै खुसी तुल्याएको छ र यो चाहिँ उहाँको रिजल्टहरू चाँडै नै देख्न र सुन्न अथवा हामीले पनि हेर्न पाइयोस् भन्ने म शुभकामना पनि दिन चाहन्छु। र यो भन्दै आजको यो कार्यक्रमलाई यहीँ सकिएको घोषणा गर्दछु। धन्यवाद।
नमस्कार।
Thank you everyone for cooperation and thank you. अब हामी छुट्यौँ है सर?
छुट्यौँ ल। अब इन्फर्मल भयो।
चाँडै नै अपलोड गर्छु यो रेकर्डिङ पनि हाम्रो सोसाइटी।
त्यो बिचमा काटिएकोलाई ठ्याक्क जोडेर गरिदिनु होला है प्लिज।
सर मैले पज गरेर राखेको थिएँ।
ठिक छ।
अनि हेरौँ के हुन्छ, पहिले एकचोटि हेर्छु अनि त्यसपछि केही एडिट गर्नुपर्ने रहेछ भने एडिट गरेर गर्छु। ओके, हामी बिदा हुन्छौँ है त सर? ल थ्याङ्क यू नारायण सर।
ओके बाइ। धन्यवाद। नमस्कार। धन्यवाद फिजिकल सोसाइटीले।
बाइ सर।